This is the game of tic-tac-toe, and I assume you have played it as a kid. The rules are simple. Players take turns placing X's and O's on the 3x3 grid. The player who manages to place 3 pieces in a row, a column or a diagonal wins the game. But how do we teach an AI system to play this game optimally? Let's assume for a second we have reached this late game state, where the O player has 2 choices left. The player can move mid-left. Alternatively, the player can move to the bottom left corner. If the O player moves to the bottom left corner, the X player has only one option left and the O player loses the game. Moving to the middle left position, on the other hand, leads to a draw, which is a much more favorable outcome for the O player. In order to teach the computer to think along the lines we just did, we need to assign numbers to different game states. If the X player wins, for example, we say that the value of the final game is +1. If the O player wins, the value of the final game state is -1. And in case we have a draw, the value of the game state is 0. Now let's work through a simple example. We assume once again that we are in a late state of the game and that it is the turn of the O player. The O player tries to minimize the outcome of the game. Preferably, this player wants to achieve -1. Therefore, we also call it the min player. There are 2 possible moves in that state: the left bottom corner and the right bottom corner. The X player has only one option left and the result is a draw. In that case, the outcome of the game counts as 0. Once the game reached its conclusion, we propagate the results to the top. That means that the previous move also has the value of 0. If we follow the other path, the X player would win the game. In that case, the game results in a score of +1. Once again, we propagate the results upwards. Therefore, the previous move also has the value of +1. At this point, we go one step upwards and compare the 2 paths. The left path gives us a value of 0. The right path gives us a value of +1. Remember that we are making calculations from the perspective of the min player. In that case, we prefer the value of 0. Making a draw is much more preferable than losing the game. Theoretically, we can go one step backwards and imagine that it is the turn of the X player. At that stage, the X sign in the middle left position is just one of possible options. Unlike the O player, the X player is the max player and preferably it wants to achieve a score of +1. There are 2 other paths that the X player could theoretically take. In the middle path, the X player chooses the left bottom corner, while in the right path, the X player chooses the bottom right corner. Let's expand the middle path first. The O player has once again 2 options at its disposal. If it chooses the middle row, the game is over and the X player loses. This corresponds to a score of -1. Now let's imagine the O player chooses the bottom row. In that case, the X player wins the game, and the score in the final state is +1. We backtrack the score to the state above and compare the 2 possible moves. And let's not forget that at this point the O player makes the decision. That means that we need to minimize the score. Given the choice between +1 and -1, the O player would much rather win than lose. So we pick the left path. Now let's do the same exercise for the right path that the X player can choose. Once again, the O player has 2 options at its disposal. The left path leads to a victory for the O player, which corresponds to a score of -1. The other path ends in a draw. This corresponds to a value of 0. and we backtrack this value to the move above. The O player chooses the minimum value of -1. At this point we have to move all the way back to the top in order to determine the optimal move for the X player. The X player is the max player, therefore we choose the left path. That leads to a value of 0. This procedure where one player tries to maximize the score and the other tries to minimize the score is called the minimax algorithm. Now let's move a step back and go to the very beginning of the game. At this point in time the X player has 9 options. So we simulate all 9 paths. At that point the O player has 8 options, and so we extend this tree further and further down until the final state where one of the players would win or there is a draw. And then we backtrack all the way to the top. If you would like to see an implementation of the minimax algorithm in Python, there is a link in the description below. Thank you for watching this video and see you next time.